In this lecture, I am going to present what is suspension cable, what is suspension bridge, and what is girder, what is 2-inch stiffening girder, and how to find out the horizontal thrust, vertical reaction, and maximum tension in the suspension cable. Also, how to find out the moment and shear at any section in the stiffening girder. Then I would like to solve a problem on suspension bridge having two cables stiffened with 2-inch girder. Then before coming to 2-inch stiffening girder, I would like to explain what is cable, what is suspension bridge, and stiffening girder. First we have to know what is cable. Cable structure is a form of long span structure that is subjected to tension and uses a suspension cable for support. Because of high strength to weight ratio, the designers use cables to construct a long span structure. In structural application, the term cable means a flexible tension member. Cable is the main load carrying member of a suspension bridge to transfer the load to support. It is a tension member capable of transmitting vertical loads horizontally by developing horizontal thrust through its shape. Therefore, the analysis of cable involves the determination of stresses in the cable as well as the shape it would adapt under given system of loads. Then we have to know what is suspension bridge. Suspension bridge suspend the roadways from huge main cables which extend from one end of the bridge to other end. Basically, there are two types of bridges, namely unstiffened bridge and stiffened bridge. Unstiffened bridge consists of floors without stiffening trusses and girders suspended from cables. But in stiffened bridge, that is consists of floors with the stiffening trusses and girders and suspended from cables. Typically, a suspension bridge consists of the following components: the main cable that suspends the bridge deck, main towers that hold the main cable, stiffening girders which are made up of solid girders or trusses and connected to bridge deck, suspenders or hangers that connect the bridge deck to main cable, anchorage which the backstay is fixed. Then what is stiffening girder? The stiffening girder constitutes the bridge deck. Its role is to keep the structure is quite stiff. It also helps to distribute the applied loads on the deck and transfer them to the cable through the hanger. There are two types of stiffening girders. One is 2-inch stiffening girders and 3-inch stiffening girders. So here we will discuss what is 2-inch stiffening girder. In 2-inch stiffening girder, there is no hinge at the center of the span, as in the case of 3-inch stiffening girder. In the case of 3-inch stiffening girder, there are having 3 hinges, 2 hinges at two end and 1 hinge at the midpoint, at the center of the girder. But in the case of 2-inch stiffening girder, only 2 hinges is present at both ends. Since the cable of the suspension bridge is the main load bearing member, the curvature of the cable of an unstiffened bridge changes as the load moves on the decking. To avoid this, the decking is stiffened by either 3-inch stiffening girder or a 2-inch stiffening girder. In 2-inch stiffening girders, the 2 hinges are provided at the two supports. There is no hinge at the center of the span. The stiffening girder transfers a uniform or equal load to each suspender irrespective of the position of the load on the decking. The 2-hinge stiffening girder is a statically indeterminate structure. Since there are three unknowns to be evaluated, namely the vertical direction at the left support, the vertical direction at the right support, and the pull W exerted by the cables. But we require three equations to determine the three unknowns. However, only two equations based on static equilibrium are available. In the case of 3-hinge stiffening girder, because of central hinge, the moment about the hinge is 0. This condition gives the third equation, and such condition is not available to 2-hinge stiffening girder. So the analysis is made simple by assuming that the girder is very stiff, and hence whatever is the load on the girder, the stiffeners are equally stressed. Equivalent UDL due to force in suspenders is equal to the average load on the stiffening girder. Figure 1 shows the typical suspension cable with 2-hinge stiffening girder hinged at the abutment A dash and B dash. So this is the typical suspension cable with 2-hinge stiffening girder. So here this is the suspension cable and this is the 2-hinge stiffening girder, and here these are the suspender, and this is the 2 hinge at 2 ends. 2-hinge stiffening girder has 2 hinges at the ends. Truss or heavy beam can be used for the stiffening girder. For stiffening girder, 2-hinge stiffening girder, so you can use the truss or heavy beam. The cable and the girder are connected by a number of hangers or suspenders. These are the hangers or suspender which is connected to the 2-hinge stiffening girder and the cable. The cable and the girder are connected by a number of hangers or suspenders. As the number of suspenders are very large, and due to the forces in the suspender, the load on cable or girder may be taken as uniformly distributed load. The load on cable or girder may be taken as uniformly distributed load. So this is the free body diagram of cable and 2-hinge stiffening girder. So this is the free body diagram of the 2-hinge stiffening girder, and this is the free body diagram of the cable. Here you see this is the 2-hinge stiffening girder, and this is the uniform distributed load WE per unit length. So what is the load is acting, that is the dead load and live load. Due to that load is distribute as a equivalent uniform distributed load. So here this is the vertical reaction at 2 end of the 2-hinge stiffening girder, RA dash and RB dash, and this is the uniformly distributed load acting on the 2-hinge stiffening girder. Here also the same equivalent UDL is acting on the suspension cable, and this is the vertical reaction at A, and this is vertical reaction at B, and this is horizontal reaction at A and horizontal reaction at B. The horizontal reaction is same at A and B, and this is the vertical reaction. Equivalent uniformly distributed load due to forces in suspender is equal to the average load on the stiffening girder. So this is the equivalent uniform distributed load. So that you can find out by taking the total load on the girder divided by the horizontal span, W by L. Then we have to go for the analysis of suspension cable. This is the suspension cable. This is the free body diagram of the suspension cable. So here this is the horizontal thrust, this is the vertical reaction. For suspension cable, the horizontal reaction H, that you can find out using this formula. The horizontal reaction H is equal to WE L square by 8H. WE is equal to equivalent uniform distributed load, that you can find out the total load by horizontal span length. So using this formula you can find out what is the horizontal reaction. H is equal to WL square by 8H. Then the vertical reaction that you can find out, the vertical reaction at the end is V. So V is equal to WEL by 2. So what is the equivalent uniform distributed load is present on the cable? So this load into the total length of the span, WE into L, WE into L divided by 2. So that is the vertical reaction at both ends. V and VB, VA is equal to VB is equal to WEL by 2. Then the maximum tension in the cable that you can find out by taking the root over of VA square plus H square. So here you can find out what is the maximum tension. So that is VA square plus H square root over, that is the maximum tension in the suspension cable. Then we have to go for the analysis of the girder. So we can find out the moment at any section in the girder, or we can find out the shear force at any section in the girder. Let take a section at a distance Z from the support A dash, and we have to find out what is the bending moment at the section at D dash. So this is the section D dash at a distance Z from the support A dash. This is the section. So here we have to find out what is the moment and what is the shear force. This is the equivalent uniform distributed load. WE per unit length, this is the load, equivalent uniform distributed load, and due to this load, this is the reaction, WEL by 2, WEL by 2. The total equivalent UDL is WE into L, and the reaction at both ends due to the equivalent UDL WEL by 2, WEL by 2. And this is the vertical reaction RA dash, RB dash. So we have to find out here the bending moment at a section D dash, at a section D dash, that is Z from the support A dash. So MD dash is equal to the beam moment plus the moment due to WE. So here you have to find out, so what is the beam moment and what is the moment due to the equivalent uniformly distributed load. So MD dash, this is the moment at a section D dash. So this is equal to the beam moment minus this is the moment due to the equivalent uniform distributed load. So here the moment due to the equivalent uniformly distributed load, that you can find out the moment due to WE at point D dash, that you can find out by considering this one, the moment from this WE that you can find out at the section D dash by taking this reaction, and this is the load. So here you have to take the due to this reaction WEL by 2. So what is the moment due to this reaction? What is the moment at D dash due to this reaction? WEL by 2 into Z, and due to this anti-clockwise rotation, so you have to take this is negative. And what is the WE present for this portion? The total load on this portion is WE into Z, and the moment about D dash is Z by 2, WE into Z into Z by 2. But the moment rotating about the section D dash is clockwise direction, so you have to take this is positive. The anti-clockwise negative and clockwise moment you take positive. So minus WEL by 2 into Z plus WZ into Z by 2. After taking the common minus, WEL by 2 into Z minus WEL Z square by 2. Then after taking WZ by 2 common, so the finally the moment at D dash is equal to minus Wz into L minus Z by 2. So this is the moment due to We into Z into L minus Z by 2. Similarly, the shear force at D dash, that you can find out by taking the beam shear and the shear due to the equivalent uniformly distributed load. So FD dash is equal to beam shear. This is the shear due to the equivalent uniformly distributed load. So here this is calculated. Here the detailed expression is given here. Shear force due to We at point D dash, that you have to take what is the load is given here. This is the reaction due to We L by 2, this is downward direction and this is upward direction. What is the load for this portion? W into Z. So this load you have to take negative downward and the upward load you take positive, minus We L by 2 plus W into Z. Minus We L by 2 plus W into Z. Then after taking the negative common, We L by 2 minus W into Z. Then after taking We common, minus We into L by 2 minus Z. So this is the shear force due to We at the point D dash. So using this formula, you can find out what is the moment at any section or what is the shear force at any section in the stiffening girder. Then coming to one problem, a suspension bridge of span 80 meter and width 6 meter is having two cables stiffened with two hinged girder. The central dip of cable is 8 meter. The dead load on the bridge is 5 kN by meter square and the live load is 10 kN by meter square, which covers the left half of the span. Then determine the shear force and bending moment at 20 meter from the left hand. So you have to find out what is the bending moment and shear force at a distance 20 meter from the left hand. Find also the maximum tension in the cable. Then you have to find out what is the maximum tension in the cable. So this is the suspension bridge, this is the suspension cable and this is 2 hinge stiffening girder. And the length of the stiffening girder is given 80 meter. And you have to find out what is the bending moment and what is the shear force at a distance 20 meter from the support A dash. Here you have to find out what is the bending moment and shear force. Also you have to find out what is the maximum tension in the cable. You have to find out what is the maximum tension in the cable here. This is the width of the roadway. This is the cross section. When we take a section here, so this is the cross section of the roadway. This is the cross section of the roadway and this is the roadway width and this is the suspender. These are the suspender, this is the suspender and this point is the cable. And here this is the width of the road. So the width of the road is given 6 meter. This is the free body diagram of 2 hinge stiffening girder and the suspension cable. Here there is having the dead load and the live load. The dead load is given 5 kN by meter square and live load is given 10 kN by meter, which cover the left half of the portion. So only the left half portion the live load is present and the dead load is present throughout the length. The dead load is given 5 kN by meter square and the live load is given 10 kN by meter square on the left half portion. And this is the dip of the cable is given 8 meter and this is the span of the stiffening girder. This is the span of the stiffening girder and this is the dip of the cable, central dip of the cable. This is also given. This is the stiffening girder, this is the dead load and this is the live load. The dead load is present throughout the span, that is 15 kN by meter and the live load is present 30 kN by meter. So how you will find out this one, the dead load and live load? How you will find out the dead load and live load on the girder? Because here you see the dead load on the bridge is given 5 kN by meter square, but the width of the road is given 6 meter. Half of the road width will goes to the one cable one side and the other half is go to the other side. So here you have to find out, so the what is the load is given, dead load or live load, that into 6/2. So the dead load per girder, that you have to find out, that is 5, what is the dead load is given, 5 kilonewton by meter square, but 6 is the width of the roadway. So half of the road width will goes to each girder. So the dead load per girder, that you can find out by multiplying 5 into 3, 6/2. So this is equal to 15 kilonewton by meter on entire span. So this is the dead load is coming to each girder, 15 kilonewton by meter. Similarly, the live load, that is also given 10 kilonewton by meter square, but what is the road width of the girder? 6 meter. So half of the road width will goes to each girder. So 10 into 6/2, so this is equal to 30 kilonewton by meter on left half portion. So this is the 30 kilonewton by meter, the left half portion, the load is present. Then you can find out what is the total load on a girder. So this is the dead load, 15 kilonewton by meter, and this is the live load, that is 30 kilonewton by meter. So what is the total load on the girder? 15 into 80 meter plus 30 into 40 meter. 15 into 80 meter plus 30 into 40 meter, this is equal to 2400 kilonewton. Therefore, the equivalent UTL, then you can find out what is the equivalent uniformly distributed load from cables. So WE is equal to total load by span. So total load is, you got here 2400, and what is the span length? 80. 2400 divided by 80 is equal to 30 kilonewton by meter. Then after knowing the equivalent uniform distributed load, this is equivalent uniformly distributed load which is acting on the suspender, suspension cable and on the girder. The same load is acting on the suspension cable and on the stiffening girder. Then you can find out what is the horizontal thrust. This is the formula for horizontal thrust. H is equal to WE L square by 8H. So WE is, you got here 30 kilonewton by meter, and L square, this is 80 into 80 by 8 into H. So this is equal to 3000 kilonewton. This is the horizontal thrust. Then you can find out what is the vertical reaction. What is the vertical reaction on the cable? This is the horizontal thrust of the cable, and this is the vertical reaction of the cable. This is WE into L by 2. So WE, you got here 30 kilonewton by meter into L by 2, 80 by 2. This is equal to 1200 kilonewton. Then you can find out what is the maximum tension in the cable. T max is equal to root over of V square plus H square. So this is V and this is H, 3000 square plus 1200 square. So this is equal to 3231.10 kilonewton. This is the maximum tension in the cable. Now consider the analysis of girder, which is subjected to a given load and to upward WE. This is the upward equivalent uniform distributed load, and this is the load is present on the girder. This is the dead load and this is the live load. And due to this load, you have to find out what is the bending moment, B moment, and due to this equivalent uniformly distributed load, you have to find out what is the bending moment and what is the shear force at the section X-axis. So at D dash, which is 20 meter from left support, so you have to find out what is the shear force at a distance 20 meter from the left support, that is at the D dash. So FD dash is equal to beam shear plus shear due to WE. So due to given dead load and live load, so what is the reaction at A dash? The reaction at A dash that you can find out. The reaction at A dash that you can find out by taking the moment about the other end. By taking the moment about the other end, you can find out what is the reaction at A dash. Similarly, by taking the moment about A dash, you can find out what is the reaction at the other end, RA dash and RB dash. So the R A dash that you can find out, the reaction at A dash is equal to moment about B dash divided by 80. So reaction at A dash is equal to 15 into 80 into 40 plus 30 into 40 into 60 divided by 80 is equal to 1500 kilonewton. So this is the reaction at A dash. Similarly, you can find out what is the reaction at B dash. So B dash, also find out what is the total load is present minus R A dash. Then you can find out what is the reaction at B dash. This is equal to 900 kilonewton. Then you can find out what is the beam shear at D dash. You can find out. Then you have to find out what is the beam shear at a section 20 meter from the A dash. What is the moment? First you have to find out what is the beam shear at D dash. So beam shear is equal to, so what is the reaction here? The beam shear you can find out here at a distance 20 meter from the A dash. So what is the reaction here? Then what is the load is present, live load and dead load for this portion. From this you can find out what is the shear force at the section D dash. R A dash, this is 1500 minus, so this is the dead load. So dead load is you got 15 kilonewton by meter, 15 into 20, and this is 30 into 20. This is 1500 minus 15 into 20 minus 30 into 20. This is equal to 600 kilonewton. So this is the beam shear at D dash. Then what is the shear at D dash due to the equivalent uniformly distributed load? So this is the formula, WE into L by 2 minus Z. Then you can find out what is the shear force at D dash. So by taking the beam shear and plus the shear force due to the equivalent uniformly distributed load using this formula. Then what is the shear force at D dash? This is 600 minus 300 into 80 by 2 minus 20. So this is you got here 0. The shear force at D dash is equal to FD dash is equal to 0. Then find out what is the moment at a section 20 meter from the support A dash, that is at A dash. So the moment at D dash is equal to empty dash. So this is also equal to B moment plus moment due to the equivalent uniformly distributed load. So the B moment that you can find out at the section 20 meter. Here you have to find out what is the B moment due to this reaction and due to this UDL. Then by considering this equivalent uniformly distributed load, also you can find out what is the moment at the section XX at a distance 20 meter from the support A dash. So here the B moment is equal to 1500 into 20 minus 15 into 20 into 10 minus 30 into 20 into 10. You have to find out what is the B moment here at a distance 20 meter from the support A dash. So 1500 into 20, 1500 into 20, and due to this dead load 15 into 20 into 10, and due to this live load 30 into 20 into 10. This is the moment. 1500 into 20 minus 15 into 20 into 10 minus 30 into 20 into 10, and this is due to the equivalent uniformly distributed load. This is the formula already we have discussed in theory portion. So WE into Z into L minus Z by 2. So here WE, this is 30 into 20, 20 Z is equal to 20, and L is equal to 80, and Z is equal to 20 by 2. Then what the moment at section D dash is equal to empty dash. So here you got this is 3000 kilonewton meter. So this is the moment at a distance 20 meter from the support A dash, and the shear force at a distance 20 meter from the support A dash is 0, and the moment at a distance 20 meter from the support A dash is 300 kilonewton meter, and the maximum tension in the cable is 3231.10 kilonewton. Now all are clear how to solve the suspension bridge that is the suspension cable with the 2 hinge stiffening girder. How to find out the maximum tension, how to find out the horizontal thrust, vertical reaction in the cable, then how to find out the shear force and bending moment at any section in the 2 hinge stiffening girder.